Hello everyone, you're welcome to this quick run through of question 4, the last of these videos that I'll be doing. Question 4 on the electromagnetism paper from 2022. Question 4, as you can see, the heading there is on induction and oscillations. And the first part, the magnetic field threading a circular loop radius 0.2 meters is given by the equation that if the resistance of this loop is 3 ohms, calculate the current flowing in the loop after 10 seconds. Apologies there. First things first, if you've got something, an expression in a physics exam that says 6t squared plus 15t plus 10, you can be pretty sure at some stage you're going to have to either integrate that or differentiate it. And that's what we're going to have to do in this calculation. I've done out the solutions already, so I'll just show you what I've written out. So I've written out the expression for the magnetic field. I've written down the information. Radius is 3 ohms. Sorry, the resistance is 3 ohms. The radius is 0.2 meters. And of course, the flux going through a circular loop is simply the magnetic field times the area of the loop. So that's pi r squared b, and then that gives you the expression there. Now the equation you're given at the end of the exam says that the EMF equals minus the derivative with respect to time of the flux. So the only time dependent part is the b part. Pi r squared doesn't depend on time, so we're going to differentiate 6t squared plus 15t plus 10. When something's raised to a power, when you differentiate it, you multiply whatever's in front of the quantity by the power and subtract 1 from the power. So 6t squared becomes 12t, 15t becomes 15, and 10 is a constant. It doesn't change with time, so therefore it has a zero differential. We get minus pi r squared 12t plus 15. So putting the numbers in, you get 17 volts. I'm ignoring the minus because that's basically Lenz's law, which says that the EMF generated opposed the change which created it, which really isn't important in this part of the calculation. Then I just use Ohm's law to work out what the current is, and I get 5.67 amps. Okay, so that's part A done. Fairly straightforward. I'm just going to slide this up now a little bit so you can see part B. So in part B, what you're asked to do is, starting with the definition of inductance, show that the inductance of a solenoid depends on n squared, where n is the number of turns per unit length. Well, the definition of inductance, n phi over I. So it's the total. Phi is, you can think of as the flux through an individual coil, and n phi is the number of turns of that coil. In the first question, we only had one turn, so we didn't have to worry about n. But now it's the total flux divided by the current. And n phi, as you see on the right hand side here, n phi is Ba times the number of turns. Ba we used in the first calculation as well. The number of turns, n is the total number of turns, which is the number of turns per meter multiplied by the length in meters. Okay. Now we know for a solenoid, a series of turns, the magnetic field is mu naught Ni. Again, where n is the number of turns per meter. So we can put mu naught Ni in for B there. So n phi B equals NL mu naught Ni times the cross-sectional area. You sub in all your values, and you get that L equals, remember L inductance is n phi b over I, so it's that expression for n phi b divided by I. You get that expression, and of course what that gives you, L depends on the number of turns per meter squared. Okay, so far so good. Now, in part C, by applying the loop rule to an LC circuit, derive an equation for the evolution of the charge on the capacitor and show that the period of resulting oscillation is given by t equals 2 pi over the square root of LC. So we have our series connection between a capacitor and an inductor. Ohm's law for what I call Ohm's law, the basic law for a capacitor, is Q equals CV. V equals Q over C, and in this case, you normally use capital Q for fixed stored charge. In this case, we've got something that's going to change with time, so you can think of Q as a function of time divided by the capacitance. Okay, so that's the EMF, or the voltage across the capacitor. The corresponding voltage across the inductor, we've already seen in a previous calculation, is minus L di dt, where L is the inductance of the inductor. Okay. Now, as we go round the loop, we get that Q over C plus L di dt equals 0. So we've got the makings of a differential equation. The L di dt equals minus Q over C. Now, we can make this a little easier, something we recognize from what we've done before. The current is dq dt. So this di by dt becomes d by dt of dq by dt. And d by dt of dq by dt is d2q dt squared. All right. And we end up with d2q dt squared equals minus q over LC. Now this is a very common second order differential equation. And the first time you will have come across this equation in this form of equation would be in simple harmonic motion, where then you had d2x dt squared equals minus omega squared x. Solutions in maths just depend on what the shape of the equation is. So these have exactly the same structure. From what you did with simple harmonic motion, you may remember that the solution that works is x equals x naught cos omega t, or x equals x naught sine omega t. Both will give you a solution that works. And there's another couple of other solutions that work as well. But if we just think about, so if x equals x naught cos omega t works for that solution, then q equals q naught cos omega t will work for this equation. It's just a matter of what does this omega represent. Here it was minus something squared times x. So minus something squared times q is what will allow us to work out omega. So omega squared must be 1 over LC. What's omega? Omega is 2 pi f. So if we square if we square 2 pi f, that's 4 pi squared f squared, that equals 1 over LC. Apologies, I just need to move this slightly now. Rearranging this, we get f squared is 1 over 4 pi squared LC. And therefore f takes the square root. 4 pi squared is simply the square root of 4 pi squared is 2 pi. LC, the square root of LC is the square root of LC. But we know that f is 1 over period. The frequency of a motion is 1 divided by its period. So we take 1 over f, and that just gives us the t. The period is 2 pi times the square root of LC. Okay. I don't think I showed you the question before we did that part, so I'll just put the question in front of you again. By applying the loop rule to an LC circuit, derive an equation for the evolution of the charge on the capacitor and show that the period of resulting oscillations is given by t equals 2 pi square root of LC. So we've done that particular aspect of the calculation. Part D. Using the appropriate equations, explain why long-distance power transfer is carried out at very high voltages. This can be a tricky, or can catch students out. So again, I'm just going to give you a very simple explanation here. A simple sorry, I need to get that down. A simple kind of work through of my explanation of this. You may have something more complicated in your notes. If you have, then that's what you should go to and refer to for John's exam, if this question should come up. So our basic equations for electricity: V equals IR, power equals VI, and of course from that you get P over V equals I. Now remember what we're talking about here. We're talking about the power losses. Oh well, the whole point of using high voltages is we want to avoid power losses in the wires that lead to the device that you actually want to operate. So for example, for a kettle, so the wires that go along the electricity lines have a long distance to go before they reach your kettle. And it turns out that if you send electricity at very low voltages, that means you're sending electricity at high currents if you want to supply that a high power. Remember, power equals VI, so if we use a very small value for V, then I must be extremely large. And why is that problematic? Because the losses in the cable depend on I squared times the resistance of the cabling. So what you want is you need a certain power at your kettle or any device. So the idea is that we use a very high voltage, which means we minimize the current. And so when you I squared R, it is I is much smaller, and so the losses are smaller. Now, high voltages are very dangerous, so you do not feed the high voltage into the home. You use a transformer near the home to change the voltage, drop it down, so that you have a high current going into the kettle. Okay, so what I've said here, to minimize loss in the cabling, electricity should be transmitted at high voltage. Yeah, so that's the explanation. Right, we move on to part E. For a resistive circuit, show that the power dissipated in an external resistor is maximized when its resistance is the same as the internal resistance of the power supply. Okay, so we're just going to assume a DC power supply. So a DC power supply, with every source of EMF, you have some form of internal resistance, which I've just labeled as little r. And this is the load resistor that's connected onto the outside. So this could either, what's in here could either be your power supply, or it could be a battery. Okay. As we've just been talking about, what's really important, it's asking you for the power dissipated. So the power in the load is I squared RL. And what's the current in the circuit? Well, it's the EMF of the total voltage in the circuit divided by the total resistance. The two resistors are in series, so you just add them up, R plus RL. And so the power in the load is going to be I squared RL. Now, we want to maximize PL. Now, obviously maximize, again, we're going to use some calculus. If you take differentiate PL with respect to RL, and set that equal to 0, that will give you the best value for RL to use. So we're going to put dPL divided by the RL equals 0. We're trying to figure out what's the best RL, so that's why we're differentiating with respect to RL. So d by dRL of all of this should be equal to 0. Now we can take the E squared out for a start, because it doesn't, it's a constant, it's a fixed thing in our circuit up here. And still set that to 0. Then how do we differentiate a quotient? Well, you just use the quotient rule. So I always learned that you just U over V is RL over R plus RL all squared. U is the top line, V is the bottom line. Okay, so U is RL, V is that squared. If you differentiate RL with respect to RL, you just get 1. If you differentiate this with respect to RL, you can either multiply that out, or you can just use a simple law where you take the 2 down here and subtract 1 off that. So that's 2 times all that to the power 1, and differentiate what's inside here. Multiply the 2 together, and it's very simple. When you differentiate what's inside, it's just 1. So you get 2 times this whole bracket. Right. There's our little formula for how you work out. Apply the quotient rule, and we end up by subbing in all the values. You get this. Now, the top line is what's important here. Okay, the bottom line is not going to be 0, so it has to be the top line. Sorry, you don't want the bottom line 0 anyway, because they'll give you infinities. But if this is going to be equal to 0, it's the top line must be equal to 0. So you multiply out everything on the top line and put it equal to 0, and you're left with that. RL squared minus R squared equals 0. So the only way that can happen is if these two are, is this up? Sorry, now I was talking ahead of myself there. So that must be equal to 0. And then simplifying it down, you get that. And of course, you've got 2RL squared minus RL squared, so that's just RL squared. And so it's clear enough, RL squared must equal R squared, and R must equal RL. And that is how you transfer maximum power to the load. It's a little bit counterintuitive because you're actually only transferring for, if RL equals R, you can work out very quickly, only half of the voltage is dropped across RL, the other half is dropped across little r. But that gives you the maximum power transfer. Okay, so that's 4E, and we have one last little bit to do, and then I'm done for the day. Part F. Show that it is possible to tune the apparent resistance of an external load using a transformer. Hint, consider the power dissipated in a resistor in the secondary circuit, and then relate back to the apparent resistance experienced by the primary coil, which is Vp over Ip. Okay, so here's your transformer, that block, the square block shape there. You have a primary circuit here. This is your source of EMF, and it's just driving current around a loop that is wrapped around one arm of the transformer. And then you have the secondary over here, loads of coils here connected to the load resistance. And the basic idea of a transformer is the voltage in the secondary divided by the voltage in the primary equals the number of turns in the secondary divided by the number of turns in the primary. Okay, and what John has hinted at in the question is that there's no obvious resistance here. Okay, this is just a source of electricity going around wire and back. So what the resistance comes from is all of this combined. What effect is this having? And it's going to be related to RL. And so the apparent resistance of the external load, this is effectively the resistance as detected in the primary. So what we're trying to work out is an equivalent resistance, which equals Vp over Ip. We want an expression for this equivalent resistance, which will depend on RL and the structure of the transformer. The structure of the transformer is basically NP and NS. So the basic starting point is assume no power loss. So Vi in the primary equals Vi in the secondary. Right? So Vp Ip, Vs Is. Now we rephrase each of these to work out an IP. So for example, for Vs equals Is RL, that's over here. This is Ohm's law applied to that circuit alone. And so the Is is Vs over RL. Similarly then, to work out IP, we're applying it to this circuit here. Now remember, we're saying the equivalent resistance in this circuit is the R equivalent. So we get Vp equals Ip R equivalent, Ip equals Vp over R equivalent. Right. We sub both those currents back into this expression here. So Vp multiplied by Vp over R equivalent, Vs multiplied by Vs over RL. Cross multiply everything to get it all, and so you're not dealing with fractions. Vp squared or L equals Vs squared or equivalent. This then gives you this relationship, and we've now got R equivalent on its own, but we haven't got things in terms of the structure of the transformer. We've got Vp squared over Vs squared. But if you look up here, we know the relationship between Vp, Vs, and Np and Ns. If you turn that upside down on both sides, Vp over Vs is going to equal Np over Ns. So we can replace Vp over Vs squared by Np over Ns squared times RL. And that's that question done. Okay, hopefully you found this video useful and the other videos that I've done. If you have any questions, just email me and I'll get back to you if I can. All the very best with your exams, and hopefully I'll see you in September. Take care.